So, in this course on gas turbine engines, aero engines, the first parameter that we discussed at the very beginning will be also the parameter that we will discuss today. It's maybe the most important parameter in everything that we discussed in this course, certainly from a thermodynamic point of view. This is the TIT. So the turbine inlet temperature, also called turbine entry temperature by the British. And so this is the parameter that we will discuss when speaking about turbines. Turbines, you have seen that already in courses on turbomachines, turbomachinery. Here we will not discuss the shape of turbine blades. This is not the objective to discuss the shape of this. The objective is to discuss how can I increase the TIT. We have continuously said from the first lesson that the TIT must be high, higher and higher and higher, the highest value possible. Because it is improving all parameters that we have discussed as the thrust, as the specific thrust, as the thrust to weight, as the TSFC, as the SFC, as all parameters that we have discussed in turboprops and turbofan, in turbojet, in turboshaft, in all engines that you can imagine. The question is, so how can you increase the TIT? In fact, this question is a kind of nonsense, because you need to relate this increase in TIT with another parameter, which is the lifetime. Because, of course, you could increase the TIT, but then the lifetime of the turbine would be very short. When we say increasing the TIT, this is at least considering that the lifetime is constant, is not decreasing. And even what we would like to have, this is an increase of the TIT together with an increase of the lifetime, which is, of course, not very well going together, because if you increase the TIT, you increase the temperature of the metal, a priori, and so you will decrease the resistance of this metal and you will decrease its lifetime. But this is the combination that we want to make, okay? And I will not so much discuss this because it is going too far away from the number of hours I have available in this course, but this is behind the scene, behind what I will discuss related to the TIT. And in fact, there are, let's say, 4 ways to increase the TIT. 4 ways to increase the TIT. A first solution is to change the materials. So improve the materials. I have discussed that with some people in another course of ULB-VUB. There is also a course at KU Leuven that is called Turbo Machines 2, where we can discuss that. But this is not the place here to discuss these new materials. But globally speaking, very globally speaking, we can say that the improvement is something like 1 degree Celsius per year, globally speaking. So in 50 years, let's say that the first gas turbines are 50 years ago, 1970, I take a number that is easy to take care of. So you are increasing here by 50K, 50K. This is what you gain from the new materials. What you can also do, and I will put that on the same curve because we are speaking, let's say, of things that are very similar, not about the same people, but the same type of people, people specialized in materials, chemists and so on, or metallurgists. What you can do at the same time, so on the same curve, I put also the manufacturing techniques. So manufacturing techniques, this is not the same as the materials, because you can produce a blade in material A, let's say Inconel, a material with nickel-based alloy, with manufacturing technique 1, manufacturing technique 2, manufacturing technique 3. These are very different things. But they are, let's say, speaking, let's say, about the same language, these people. And there you can also say the same. Also about 1 degree Celsius per year. So in 50 years, you increase the situation by 50K. And so you see that the progress that you made in 50 years from the 60s, let's say, is something like together, these two together, 100K. 100K. If you take thermodynamics, what you've done during weeks and weeks with the assistants, making some thermodynamic calculations, 100K, it's not so much. It's not so much. So, is it improving the situation? Yes, but not a lot, not what we are certainly expecting. So, what is then the game player? What is changing totally the situation? If you take, let's say, the 60s, at a certain moment, at the beginning, I have represented in white here the curve of the material temperature. This is the material temperature. At the beginning, I will represent it in red. The gas temperature was following the curve of the material. The gas temperature was the same as the temperature of the material. They were in contact with each other, and they were, let's say, changing at the same time with the same value, with the same temperature. But at a certain moment, someone invented a way to separate these two curves. And what has this person invented? He has invented cooling. Cooling. So what has he invented? I will take an example here with a nice example. So you see the blade that is here in front of me. So this is a rotating blade. So a rotating blade, it's a blade, not a vane. This is a vane, non-rotating, and this is a blade, rotating. What do you see? The blade is empty. So the blade is perforated from the hub, from the root, and going through the tip with something, it's air, I will explain it later on, flowing inside, and so extracting the heat coming from the hot gases through the cooling of air that is escaping through the hole here, the blade taking a part of the heat transmitted by the hot gases. This is cooling. At that moment, you separate the curve of the temperature of the gases from the temperature of the material. And of course, this technique of cooling has been improved and improved and improved. And in fact, there have been different improvements. So of course, there are small improvements. Let's say that they are playing with small parameters, there's roughness or things like that. So increasing a bit the situation, but there have been at certain moment really a new technology of cooling that has been introduced. And I will describe you, in fact, 3 technologies of cooling that are changing, that have changed the situation. And so if you take cooling technology 1, cooling technology 2, cooling technology 3, and here, of course, you are also improving the situation. And there, it's a huge difference compared to the 100 that you have here. It's maybe not on scale on the drawing, but here you can reach a tremendous increase of the TIT, because the TIT, this is TG, because the TG is not anymore equal to the material temperature. And this is the first technique, the materials, the second technique, the manufacturing, the third technique, this is the cooling. And on top of that, rather recently, let's say 20 years ago, manufacturers, also material specialists, maybe not the same as these ones, but also material specialists. These ones are more aerodynamicists. So they have invented, on top of cooling, something that is able to change the curve. You see, you are not following the curve anymore of the evolution of cooling. You are introducing a force technique that is on top of cooling, also changing the situation. This is what I will call TBCs, thermal barrier coating. Thermal barrier coating, that are coatings that you put on the blade, with a material that has a much lower lambda, the heat conductivity coefficient. A much lower lambda, the heat conductivity or conductibility coefficient, so that you are transmitting through the coating that you have here on top. I don't have a blade with coating, so it's a ceramic coating that you put here on top, so that you are transmitting, you are transferring less heat to the material. And if you use it with cooling, so this heat is extracted out of the blade, and you are stabilizing for a certain TIT, the temperature of the blade at a lower temperature, or if you have a fixed temperature of the material of the blade, the TIT can be higher. And there you can also gain something like, in order to take easy values, something like 100K. So that means that thanks to the materials, you have increased the temperature of the material by 100K, and you have increased the temperature of the gas on top of the materials by 400 plus 100. So you see that TG is, let's say, something like TM plus 500K. This is what you have. I will, in this course, I will mainly speak about this, the cooling. It's not the objective to speak about the materials, it's not the objective to speak about manufacturing, it's not the objective to speak about thermal barrier coating. This is the objective to understand exactly what's happening with cooling technologies and what are these 3 steps that I have discussed here. Okay? So you need to understand what's happening. So you take a blade, a very easy model of a blade that is, let's say, a rectangular profile. Here you have the disc somewhere, and here you have the shaft that is at a certain distance from the blade. So if you take a small section of the blade here, from here you can consider the variable being R, and from here you can consider the variable being H, the height of the blade. And so here you have a certain dH equal to dR. And here around you have Tg. And the material, this is Tm. And here you have, entering into the blade, a certain air, a cooling air, at a temperature that I call Tk. At the hub, so this is the hub, this is of course Tk hub. And you see what's happening.